Hello, hello, hello. Can anyone hear me? Hello? Anyone out there? Anyone? Can anyone hear me? Anyone out there? Oh, hello. Hi. Hi, Maya. Hi, Surinder. I can see that Kathleen is here. Hello, hello. Hi, Vikesh. Hi, Delilah. Hi, hi, hi. Hello, Preppy Tropical. Hi, Stephen. Hi, Kadoa. How are we all doing this evening? Everyone okay? Everyone feeling like they fancy doing a bit of physics this evening? I thought we would do the basics of electrical service. Sorry, your name is Taryn. Hi. Sorry, I'll try and remember that. Okay. So what we're going to do is we're going to do some of the basics of electrical circuits this evening. Okay. But I'm just going to introduce myself first. So my name is Hannah Shooter. Okay. So I am a teacher of physics. I've been a teacher of physics since 2018. I have 7 years of teaching experience. I've taught a range of schools, including one of the UK's leading independent schools. I've taught at Rideridge Comprehensive Schools. I've taught at everything. Okay. I have a master's in education from Cambridge University, and I have a master's in physics from the University of Bristol. So I know what I'm doing with both physics and with education. Okay, right. So let's jump in with what you know. Now, some of you might have done things like this at school. Some of you might not have done things like this at school. So I just want to gauge what you know. So can anyone list anything that we might use electricity for? Can anyone tell me anything we might use electricity for? If you can't write in the chat, it might be because you need to subscribe to my channel. Oh, we use electricity for microwaves. Brilliant. Okay. Lights. Devices. Toaster. Brilliant. Anything else? Nothing else we use electricity for. Phones. Amazing. Yeah, for technology. Yeah, electric bikes. A niche reference, but love it. Electric bikes. Perfect. So we use electricity to transfer energy from one place to another. Yes, electric cars, amazing. So we use electricity for anything that requires energy to be transferred from one place to another. So let's have a go at our second question then, shall we? Can anyone tell me what electricity travels through? Hello, Rubik's Cube girl. Hello. Can anyone tell me what electricity travels through? Anyone got any ideas? Oh, I like that, Maya. It travels through a conductor. Lovely. So a conductor is anything that allows electricity to flow. Anyone know the opposite of a conductor? Something that doesn't allow electricity to flow? Oh, good. Well done, Vikesh. We've got that conductors are often made of metals. Made of metals. Insulators, amazing. So you might have heard of conductors and insulators before. So conductors allow electricity to flow. Insulators don't allow electricity to flow. Absolutely fantastic. Right, so someone said, I think it was Taryn said, that what we do is we draw conductors into wires, which we do. We stretch them out into long, thin wires. Does anyone know which metal most of our wires are made of? Oh, very good. We make most of our wires out of copper. So wires made out of copper. Perfect. Okay, so we make most of our wires out of copper. We choose copper because it's got a low resistance, so current flows through it really well, electricity flows through it really well. It's reasonably cheap, and we can draw it out into loads of wires. Okay, yes, loads of teachers are doing free courses this week. Not all of us, but some of us are, because the main course doesn't start until next week. Okay, right. So what does a conductor do then? Who knows what a conductor does? What could we say that a conductor does? Oh, I like that, Vikesh. Very well done. It lets electricity, yeah, flow. Lovely. I really like that. It helps electricity, or the flow of electric charge. It allows electricity to flow. Carries electricity from place to place. Absolutely amazing. Helps electricity to flow through. Fantastic. These are all really good answers. And what it's telling me is that you guys actually have got an idea of how electricity works. So I think we're going to have a really, really fun lesson. Okay. So let's start with the atom. Okay. So the atom is the building block that makes up matter. Does anyone know roughly how big an atom is? Anyone got any ideas? You learned this in year 6 about the atom. Amazing, fantastic. So some people will have done it at primary school, some people won't have done it at primary school. Some people might have done it already, some people won't have done it already. Microscopic. Oh, what a good word. Love that. Okay. Oh, yes, you're absolutely right. Very good. 300 picometers, which would be, if we wrote it out, be 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 3 meters. So really, really tiny. That's about the width from the atom from here to here. Now, not all atoms are the same size. Some are bigger, some are smaller. So we say that the atom is the building block that makes up matter. Now, from the time of the ancient Greeks until about the 18th century, what people thought is that the atom was the smallest possible piece of matter. That's where the term atom comes from. It comes from the ancient Greek atomos, which means indivisible. So the idea that if you took a piece of paper and tore it in half a whole load of times, eventually you'd reach something that you can't tear any further apart. And that is the atom. But we actually discovered in sort of the 19th century that the atom is actually made up of 3 smaller particles, okay? And these guys are called subatomic particles. Can we create an atom? Interesting question that you asked there. What do you mean by create an atom? We can cause 2 smaller atoms to fuse together to make a bigger atom. So yes, in that way we can. But we can't really like grab one proton and grab one neutron and sort of smash them together. Well, yeah, it's difficult. It's difficult. We can sort of make atoms, but we can generally make them from atoms that we've already got. Okay, so the atom is made up of 3 subatomic particles. They're called the proton, the neutron, and the electron. Okay, so have you heard of any of these before? Drop me a Y in the chat if you've heard of any of these before. Proton, neutron, electron. Drop me a Y in the chat if you've heard of any of these before. Yeah, some of us have. Amazing. Okay, fantastic. Looks good, yeah, okay. So we all kind of know what's going on here. So, if you're enjoying this stream at the moment, then do me a favour, please, because we've only got about 20 people on it at the moment. Could you please copy and paste the link at the top of the page to a friend? Okay? If you're enjoying this at the moment, copy and paste that link at the top of the page, send it to a friend. Right. Let's talk about these subatomic particles then. So subatomic means smaller than the atomic scale. So the proton and the electron have both got a charge. Okay. A proton has a positive charge, which is +1. An electron has a negative charge, so -1. And we say that like charges will attract to each other. Now, this word like means, that's actually wrong, isn't it? No, sorry, like charges will actually repel from each other. My slide is wrong. You're going to want to change this in your notes as well. Like charges will repel each other. So like charges just means the same. So two like charges would be positive and positive, or negative and negative. Okay, bye-bye if you're heading off now. Right, and then we would say that unlike charges will attract to each other. So positive charges and negative charges will attract to each other. So let's have a little bit of a check and see how much you have understood. Are you ready? So I'm going to show you two charges on the screen. I want you to pop an A in the chat if you think they attract, a B in the chat if you think they repel. Everyone okay with that? A if they attract, or let's do R. R if they repel, okay? Just pop it in the chat for me. So, are you ready? We're going to start with two negative charges. Pop an A in the chat for me if you think they're going to attract towards each other. Pop an R in the chat for me if you think they are going to repel. Okay, good, excellent, excellent. Well done, Maya. Well done, Vikesh. Well done, Delilah. Well done, Rob. Well done, Taryn. Well done, Frank. Well done, Stephen. Well done, Coyote. Really good. So these guys are going to repel. Can anyone tell me why these charges would repel? What is the reasoning? What's the why as to these charges would repel? We would say because they have the same what? Oh, because they are like, lovely, because they are like charges. Or what's another word we could use instead of like? What's another word we could use instead of like charges? Two negatives don't make positive? Yeah, okay, fair enough. What could we say instead of like charges? What kind of word could we use instead of like charges? Good, Maya. They are the same. So they are the same charge. Absolutely brilliant. Okay. Yeah, they've both got negative symbols. So that means they're the same charge. They're going to repel. We can think about this as being very similar to magnets. Okay. So we know that magnets, we know that the north and the south will attract. We know that north and north will repel. And we know that south and south will repel. So we can say the same thing with magnets, that unlike poles will attract, like poles will repel. It's really similar, okay? Except we're not dealing with magnets, we're dealing with charges, okay? Now, this is all going to come together in a minute when we start talking about electricity and why electrons move in wires. But let's have another go. Okay, so we're going to do attract or repel again. What do you think these charges would do? Are they going to attract, so A, or repel, R? Pop it in the chat for me. Good. The K's Ways. What a brilliant name. Fantastic. Well done, Maya. Well done, Stephen. Well done, Tropical. Well done. Is that Mariah? M-A-R-I-J-A? Is that Mariah? Well done, Delilah. Well done, Taryn. Well done, Coyote. Well done, Vikesh. Amazing. Really, really good. So these guys are going to attract. What's our reasoning here? Why would these guys attract? What's our reasoning? Good, because they are opposite charges. And different charges attract. Really good. They're different charges. Fantastic. I really like how we're building the explanations here in the chat. That's lovely. They're opposite charges. So, so good. This is looking really good, guys. Right. Final one. Attract or repel. A or R. Attract or repel. Pop it in the chat for me. Attract or repel. A or R. Good. 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 Well done, Maya. Well done, Maria. Well done, Delilah. Well done, Preppy Tropical. Well done, Bear. Well done, Taryn. These guys would repel, okay? They would repel because, again, they have the same charge. And we know that like charges will repel, just like magnets. So, let's apply this to electrons in wires, shall we? So, in a wire, we have got metal atoms and some free electrons. There's another word for free electrons, which is known as delocalized electrons, which some of you might have heard of before, but if you haven't, don't worry. What we mean by a free electron is that they're not orbiting a specific atom. They're just free to move throughout the atoms in a wire. And this is what makes metals such good conductors of electricity, because they've got lots of these free electrons that aren't bound to specific atoms. So they can just move through the wire. Now, we're going to talk today about using cells to power our circuits. This is a cell. Does anyone know another name for a cell? Can anyone think of another name for a cell? If I showed you this, what would you instinctively want to call it? Yeah, a battery. Okay, so we call them in everyday life. We might say, oh, that's a battery, but actually that's a cell. When we join a couple of cells together, so two or more cells together, that becomes a battery. Okay, yeah, so actually all those Duracell adverts, they're actually wrong. It's only a battery when you join two or more cells together. Okay, so I'm going to refer to this as a cell. Okay, that's what I'm going to refer to as a cell. So you might have seen that they've got a positive end at one end, which means they have a negative at the other end. So when we connect it to a wire, it makes the electrons move away from the negative end and towards the positive end. Because does anyone remember what charge we said that the electrons have? What charge does an electron have? Anyone remember in your notes? What charge does an electron have? Have a look back in your notes if you don't know. It's negative. Good. It's negative. Excellent. So these negative electrons, will they be attracted or will they be repelled from the negative end of the cell? The negative electron, is it going to be attracted or repelled from the negative end of the cell? Negative and negative, what do we know about two negatives? Good. It's going to be repelled. Brilliant. Well done, Kay. Well done, Delilah. Well done, Taryn. Well done, Maya. This electron is going to be repelled. And the electron is going to be repelled from the negative end. And it's going to be attracted to which end? They're going to be repelled away from the negative. And they're going to be attracted to which end? Which end are they going to be? Good, Kay. They're going to be attracted to the positive end. Amazing. So we get all my electrons flowing in the same direction. And this is sometimes referred to as a current. Okay? This is what we're going to call a current. It's just the movement of electrons through a wire. What happens if you use a bigger battery? A bigger cell, or you use several cells joined together in a battery, is you get a bigger positive end and a bigger negative end, so the electrons will move more. That's all it is, okay? That is all it is. So, we're going to have a quick chat about circuit diagrams. I'm not sure how many of you have seen them before. If you have seen them before, amazing. If you haven't, I'm going to teach you what this is now. So, which way do you think is the most sensible way to draw a circuit diagram? Do you think it should be A? Or do you think it should be B? Which way do you think is the most sensible way to draw a circuit diagram? Okay. Good. Everyone's saying A. Why would I personally, who's very bad at drawing, why would I choose to draw my circuit diagram like A rather than like B? Why do you think I might choose to draw my circuit diagram like A rather than like B? Taryn, I agree. It's more simple, isn't it? It's easier, easy and efficient. It's simple. B is quite complicated. It's going to be easy for me to draw. And if we use the same symbols everywhere in the world, we can interpret circuit diagrams from anywhere in the world. They don't just have to be English circuit diagrams or British circuit diagrams or even European circuit diagrams. If we all use the same symbols, we can interpret circuit diagrams from anywhere in the world. So these are 6 main symbols that we need to know. Does anyone know any of them? If you know any of them, stick the letter and what it is in the chat for me now, if you know any of them already. Anyone know any of these already? A is a switch. Well done. Very good. Any of them that you know, just pop the letter in and tell me what it is. D is not a buzzer, but it does begin with a B. C is actually a battery. F is an ammeter. Very good. Well done, Delilah. Well done. B is a cell. Well done, Maya. D is a bulb. Super. Super duper. Anyone know what E is? A voltmeter. Well done, Maria. Perfect. It is a voltmeter. Okay, super. So a switch connects our circuit, allow currents to flow. A cell and a battery provides my positive end and my negative end, sometimes called a potential difference. D is a bulb, like a light bulb. I'm hoping we all know what one of those is. E is a voltmeter. It measures the difference in energy at different points. We're not going to talk about voltmeters too much today. F is an ammeter. F measures the current in a circuit, and we're going to talk about A for ammeter quite a bit today, okay? I'm just going to give everyone 1 minute to get those written down in your notes, and then we're going to move on. So these are your, yeah, perfect, well done, Taryn. An ammeter measures the current. Absolutely amazing, okay? That's really good knowledge. I understand that for some of you might be like, oh yeah, I do know this, okay? And I'm sure that some of you do, but because we're just like coming together for this one stream today, I want to make sure that everyone's on the same page. So let's do a little memory test, shall we? Okay. What is the symbol on the screen? Answer in the chat. 3, 2, 1, go. Tell me what symbol that is. Yeah, a motor can come in a circuit, but we're not going to talk about those today. Oh, well done, Jasmine. Perfect. The first one to get it right. It is a cell. Absolutely spot on. Okay, right. Fingers on the keyboard again. We're going to do another one. Are you ready? What's this? Jasmine again. Amazing. Well done. It is a bulb. Fantastic. Everyone's getting it right, but Jasmine was the first. That is brilliant. Well done. Okay, right. Let's see if Jasmine can make it 3 out of 3, or let's see if someone's going to get there faster than her. Are we ready for number 3? What is this, please? Oh, so on my screen, they literally flashed up at the same time. Jasmine and Kyoda, they flashed up literally at the same time, but spot on. This is an ammeter. Amazing. Loads of us getting this right. This is great. I'm thrilled. Okay, right. We've talked about an ammeter. We've said it measures current. Let me talk to you now about what current actually is. Okay, so current is the amount of charge that flows past a point in 1 second. Okay. Now this amount of charge bit here, we can think of that as being the number of electrons. Because electrons have a charge, they're negative. So the amount of charge, we can think of that as being like the number of electrons that flow past a point in 1 second. Okay? Now we measure the current in this unit here called amps. It's short for amperes, and we sometimes give it the symbol A. So you know how meters, if we're measuring distance, we sometimes write that as N. We can write amperes or amps as just a capital A. Now, I like to think of current as being a little bit like runners in a circuit. Okay, so the runners start here, pick up an energy drink. This is like the cell. And they run around the circuit. Okay, now if 10 runners pass this point here, if I were to go over here, 10 runners would also pass that point there because they're in this circuit. So if 10 runners go past this point, 10 runners have also got to go past this point. And that's very similar to electrons in a circuit, okay? They all have to follow the same path and they all go at the same pace, okay? Electrons have to move at the same speed. They can't overtake each other. You can imagine this as imagine you're standing in a circle with a group of friends and you've got a loop of rope in between you, okay? So you pass it through your hands. If someone speeds up, this is for a series circuit, great, we'll come on to series and parallel circuits in just a minute. But not everyone's going to be familiar with that terminology yet. So if you're passing the rope round your hands, so you've got circle rope and friends, you're passing it through your hands. If one person speeds up, everyone's got to start moving it faster. If one person slows down, everyone's got to start moving it slower. The speed has got to be the same all the way around the circle. And we can think of this as being a bit like current, okay? So there's a lovely animation here, which I'm going to show you. I've actually got it linked in your notes, which shows us what electrons in a wire look like. So I'm just going to pop some electrons in a wire here for you. You guys can have a go at doing this in your own time if you want. This is called PhET. It's really fun to play with. I'm going to link these guys up in a circuit and we can see the electrons moving through the cell, through the wires, but they're all going at the same pace. Yes, I love PhET as well. I think it's absolutely amazing. I absolutely love it. I think it's honestly just the best thing ever. Okay, so you can see that there. You're very welcome to have a play with that. It's called PhET. In your note that you got sent for this session, that actually, where it says animation, it's actually linked there. So if you click on that link in the notes, it should take you straight to this website, okay? So it's called PhET, P-H-E-T. And if you search electrical circuits, it's really, really cool. Okay, we're going to have a look at that again in a minute, possibly. So we say that the current will be the same everywhere in what we call a series circuit, okay? A series circuit is a circuit where all the components are connected in one complete loop. So it starts with my battery at the top, all my components are connected all the way around, okay? So if my current at this ammeter here, let's say that was 3 amps, could anyone predict for me, given that I've told you that the current has to be the same everywhere in a series circuit, what the current would be here? What would the current be here at ammeter 2? If the current ammeter 1 is 3, good Maya, good Kay, very well done. It has to be 3 amps here. Oh, brilliant, well done Delilah, well done Taryn, well done Preppy Tropical, good. How about ammeter 3? How about ammeter 3? What should the current still be there as well? Very good, Kay. First one to answer. Good, Maya. Good, Maria. Good, Taryn. Well done. this should be 3 amps as well. Perfect. Because the current has to be the same everywhere in a series circuit. Right. I'm going to start a little poll. I'm going to ask you a question and you're going to tell me what the answer is, okay? There are 3 possible answers. You can either have A, B, or C, okay? So I'm going to create a poll. We're going to have A. Oh no, you can have 1, you can have 2, or you can have 3, okay? So that's the poll, and now I'm going to flash up the question for you. So the current at A1 is 1.5 amps. What would the current at A2 be? What would the current at A2 be? So click number 1 if you think it's 3 amps, click number 2 if you think it's 1 amp, click number 3 if you think it's 1.5 amps. Going to give everyone 1 more second just to think about it. The current should be the same everywhere in a series circuit. Should be the same. Very good. Well done, 82% of you who got that. Very well done. That it should be number 3. If the current is 1.5 amps here, the current will be 1.5 amps there. Taryn, you let us down. You're ruining the class average. Honestly, don't worry about it. Okay, so let's have a look at a different type of circuit then. So this is known as a parallel circuit. Okay, so this is a different type of circuit and it's known as a parallel circuit. So in a parallel circuit, the electrons can travel down different paths, or what we sometimes call multiple paths. Okay? And that means that the current splits at the junction. So if we have a look at FET, this would be like, I'm going to unclip that there. We're going to build the circuit in here, and then we're going to build a second path for these electrons to go down. Okay? So we're building it like this, and then like this. Now, keep your eye on this junction for me, please. Keep your eye on this junction for me, please. What do you notice about the electrons? What do you notice about the electrons and the pattern at this junction here? Can anyone tell me what they notice? Some are going down. Good. Some are going through or going down, or some are going one way, or some are going the other. Good. They're going different ways. Amazing. Okay. This is looking good. So you can see that that one goes that way. 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 So they're kind of taking it in turns, aren't they? One's going one way, one's going the other way. One's going one way, one's going the other way. So what could you say about the number of electrons going through each bulb, do you think? Would it be the same, more, or less? What can you tell me about the number of electrons going through each bulb? The same, more, or less? Oh, excellent. It would be less. Absolutely fantastic. They'd be the same as each other, but there's less electrons going through each bulb than there is coming out of the cell. That's great, okay? So let's take this back to our runner analogy, shall we? Okay, so let's imagine we've got 10 runners coming out of the cell, okay? So 10 runners have got their energy drinks. They're going for their run, okay? Now, how many runners would I expect to have here? How many runners would I expect to have at this point here? 10 runners got their energy drinks coming out the cell. How many runners would I expect to have here? Good, Delilah. Good, Kay. Good, Taryn. Good. It's still 10, isn't it? Because they've not split yet. You right, Bear? So 10 runners come out the cell here, and they go down here. Because there's no other path for them to travel through yet. No other path for them. They all have to follow each other. They all just have to follow the person in front of them. But then, they get to this junction here. And we're going to suggest that half of them go that way. Let's say that 5 of them go that way. How many go the other way? 10 runners. 5 go this way. Good, Maya. Good, Taryn. Good, Coyote. Good, Bear. Excellent. Good, Delilah. 5 runners are going to go this way. Perfect. So, how the runners split is actually due to something called resistance, okay? Now, resistance is something that just impedes the flow of a circuit, okay? It just slows down the current. Now, bulbs have got resistance in them, okay? So bulbs will slow down these runners, okay? Are all classes in YouTube? Yes, they are, okay? So what they're going to do is the bulbs are going to slow down the runners. Now, when we get that back to this point, though, 5 runners from this path and 5 runners from this path, how many runners would there be here then? Those 5 runners have met up with those 5 runners. How many runners would be here? 10. Good. Perfect. They're recombining. So let's just go back and have a look at our FET animation again. So we can see here that we're recombining. We're recombining here. Can you see that? That the electrons are joining back up together at this point here. Okay? So this is a really important point. The current should be the same here and here. Before my electron split and after they recombine. When does this lesson end? It ends at 7:50, but about 7:40, what I'm going to do is I'm going to just stop so that I can answer any of your questions that you might have about my Edspace, and so that I can show you a really exciting deal that we've got coming up for you guys because you've attended this session. Okay? So, here and here, my current should be exactly the same. Okay? So, what we say is the electrons can travel down what we call multiple paths. This is what we mean by a parallel circuit. It's where the electrons have got multiple paths to travel down. We say that the current splits at a junction, okay? So that the current will split at the junction and recombine at the other. If we have a look at the animation here, I've got a current of 1.8 here. So can anyone predict for me what my current would be in the wire here? Looking at our example with the runners, if it was 10 here, it was 10 here. If it's current is 1.8 here, what should it be here? Good. Amazing. That's really good. It should be 1.8 here. Good, Tara. Good, Delilah. Good, Coyote. Really good. Right. Can anyone predict for me then? Current's 1.8 here and 1.8 here. What would the current be if I were to put my ammeter here? Can anyone have a go at predicting for me what the current would be if I were to put the ammeter here? Oh, okay, we've got 2 contrasting answers here. Anyone else like to weigh in? Okay, some interesting answers. Okay, who can explain it for me? Who thinks they can explain why their answer is what they've put? Who thinks that they could explain why their answer is what they have put? Half it, okay. Why would we half it? Why would we half it? You're right. if we take the current there, it is 0.9, it is half. Why would we half it? Good, well done, Taryn, because the electrons are splitting at the junction. Half are going to go one way, half are going to go the other. Right, okay, the current is the same in a series circuit, okay? So the current will be same everywhere if the circuit is connected in one loop. In this parallel circuit, we've actually got two loops. The electrons can go this way, or they can go this way, okay? So we've got two loops in this circuit, okay? But that's absolutely fine. Good, it's 0.9 because the electron's half at the junction. At the junction, they split. So if the current is 0.9 amps here, what should the current be here in the other branch? What should the current be in the other branch? Very good, Maya, very good. It should be 0.9 there as well. Fantastic, guys. This is good. This is really good. Right. Do you want me to give you a bit of a challenge? Do you want a bit of a challenge? Who feels like they could handle a bit of a challenge? Anyone? Drop me a little Y in the chat if you feel like you can do a challenge. Yeah? Okay. Right, you ready? You ready? I'm going to make this a bit more difficult for you. You guys are really killing it today. You're so, so good. You're so on it. There, come on. Let's have some positivity here. You can make this work. Vikesh, I'm sure you can do this as well, okay? You learn lots from being challenged. Right, I'm going to turn up the current. Then what I'm going to do is I'm going to change the resistance in this bulb. Okay? What I'm doing is I'm going to make, so these are now not equal bulbs. This one at the bottom is shining brighter than this one at the top. I'm going to make that a bit more obvious. There we go. This one at the bottom is shining much brighter than this one at the top. The current here is 1.15 amps. The current in this branch here is 0.15 amps. Who can predict for me what the current would be if I were to put the ammeter here? Who can predict what the current would be here for me? Delilah, amazing. Preppy Tropical, absolutely brilliant. Any others? Maya, fantastic. Taryn, brilliant. Kay, fantastic. Bear and Vikash, would you like to have a go? Or are you feeling like you just want to watch and see how this one goes? Maria, brilliant. So well done. Fantastic. Who can explain for me why the current would be, you're absolutely right, 1 amp here? Good, Vikash. Well done. Absolutely fantastic. Okay, don't worry about it. We're going to go over it now. Don't you panic, okay? Who can explain for me why the current should be 1 amp here? Who can give me an explanation? You might like to use a bit of maths in your answer. That could help. Oh, I like that. The difference between here and here, good, is 1. The total current, I really like that, Delilah. The total current is 1.15. If this one is what, 0.15, these two have got to add together to make 1.15. Think about a running analogy, okay? So let's go back to our runners. Let's say that 10 runners came out my cell. If only 3 of them go this way, how many of them must go this way? If 10 runners come along, if 3 go this way, how many must go this way? Taryn, good. It must be 7 that go that way. Amazing. Hyoda, are you a bit more okay with us here now? Yeah? That if 3 go this way, 7 have got to go this way. This is absolutely brilliant. Really well done, guys. I'm really impressed with how you've managed that challenge. That's so, so good. So instead of thinking about it in terms of runners, we can think about it in terms of electrons. So if 0.15 electrons per second are going this way, 1 electron per second must be going this way. We must be getting this split here. So 1 plus 0.15 would go back to our original current of 1.15. Righty-ho. Are you ready? It is poll time. So we're going to do a 1, a 2, add an option, 3, go, go, go. So A1 up here is 3 amps. A2 here is 2 amps. So what must this current here be? What must this current here be? Did someone click the wrong one? I'm going to be so upset if someone clicked the wrong one. Okay, think about it in terms of runners if you need to. Think about it in terms of runners if you need to. If I've got 3 runners here, if 2 runners go this way, how many runners would go this way? 3 runners, 2 runners go that way, how many runners would go this way? This is looking very good. Very well done. 78%, nearly 80% of you, very good. Got that it should have been 1 amp. Okay, so if 3 runners come out the cell, if 2 go that way, 1 goes that way. Well done, Coyote. You're so getting this now. You're going to be brilliant at this. You're going to be so good at this. Okay, right. Tara, did you hit the wrong one? Did you do the wrong one? Right. Are you ready? I'm going to flash another question up for you. Okay. I'm going to flash another question up for you. I've started the poll. I'm going to flash another question up for you. Fingers on buzzers. Remember, no reflexive polling. Okay. Again, always again. This is how we learn stuff. We have to do it 3 times. Right, here we go. You've got A1, you've got A2, you've got A4. I want you to tell me what A3 would be, please. Okay, I've got 2 votes, 4 votes, 5 votes, 6 votes. Back to 6, 7, ooh, 5, 8, 9. This is looking good. Any more votes? 10 votes. Ooh, looking good. Any more? Come on, there's 21 people on here. I reckon we can all have a go at this. Think about it in terms of runners, if that makes it easier. If you've got 4 runners coming this way, 2 runners go this way, how many runners are going this way? 4 runners here. You can always redo the poll, by the way. If you think you've clicked the wrong answer, you can always redo it. So 4 runners coming out the cell, 2 runners go this way. How many runners would go this way? This is looking good. 12 votes. Any more? Any more? I'll end the poll. Well done to those of you who got that it should be number 2. Brilliant. Okay. So I've got 0.4 amps here, 0.2 here. It should be 0.2 amps here as well. Brilliant. And then they would recombine again, 0.2 and 0.2 to make 0.4. Well done to everyone who got it right. That is absolutely brilliant. Okay. Right. One final task. Okay. This is a tricky one. Are you ready? This is actually a really tricky one. I reckon that about 50% of my GCSE class would get this wrong. Okay. So if you guys can do this in year 8, you are going to be all over this. Okay. I'm going to do you a poll again. So if all the bulbs in the circuit are identical, what would B, C, and D read? If all the bulbs are identical, What would these read? Delilah, you think that's easy? That is brilliant. That just shows how good you are. I'm incredibly impressed by this. For like year 8, you guys have absolutely smashed today. You have done so well. You've done really well. Okay. Think about it in terms of runners. If in doubt, always think in terms of runners. If in doubt, always think about runners. If 6 runners come out here, and these are identical, we would expect the same number of runners to go down each path. We'd expect the same number of runners to go down each path. How many possible paths are there for them to take? How many possible paths are there for them to take? Can anyone tell me how many paths there are? How many ways could these electrons go? Yeah, there's 3, isn't there? There are 3 different ways. So if the electrons can go 3 ways, we're going to take our 6 amps, divide it by 3 to get 2 amps. So B, C, and D should all be 2 amps. Really well done to the 50% of you who put number 3, okay? Because that is 2 amps, okay? That is really good, okay? I reckon, yeah, but half my GCSE class couldn't get that right, okay? So that is really, really good, guys, that you've got this locked out.